Welcome everyone to this lecture on the subject of VLSI design. This is lecture number 7 and we are going to discuss the topics for today as transient analysis in interconnects and some RC delay models. Okay. So, when we talk about transient response or transient analysis, the first thing which tends to come to mind is a variation in some kind of a signal with respect to time, which is not completely wrong. Okay. Most of us have worked in labs, and whenever we connect circuits or measuring equipments, whether analog or digital, in analog measuring equipments we sometimes see the needle jumping initially and then settling to some kind of a value. In digital instruments also initially numbers tend to change a lot and then they become stable at a certain value. Okay. So, this is something which is known as, which is short lived with respect to time, is known as a transient in a circuit. Okay. Specifically with reference to VLSI circuits, okay, where you have high density integrated circuits, where lot of logic is connected or diffused on a small piece of silicon in a very small area and connected with a piece of wire. A very important parameter associated with these ICs is the capacitance. Okay. We have seen in earlier lectures that this capacitance can be the diffusion capacitance between two doped layers in an IC, or it can be the capacitance between a wire and the ground plane, okay, or a fringe capacitance between two neighboring wires. Right. So, wherever there is capacitance, there is going to be some amount of charging and discharging which is going to take place. Okay. And the time it takes for this capacitor to charge or for this capacitor to discharge is what produces some amount of a delay inside the circuit. Okay. Even if we talk about digital ICs where we provide some DC input, and when we reverse the polarity of that DC, the output does not switch instantaneously, it takes some amount of finite time. And when you apply an alternating current, an AC source to an integrated circuit, now an AC source is going to be a function of time, it varies with respect to time. So, it shifts from one level to another, it shifts from one polarity to another, from positive to negative, negative to positive. So, the output parameter may or may not be able to completely follow the input almost instantly, okay. Especially at high frequencies when the time of switching is very fast, the same speed may not reflect in the output. So, this cycle of continuous charging and discharging of a capacitance inside an interconnect is what produces some kind of a delay. Okay. So, our aim is to arrive at some kind of a model where you can quantify this time which it takes for the signal to reliably appear at the output. Okay. So, this is done by defining a differential equation for the output voltage, which is going to be a function of two things. It is going to be a function of input voltage and it is going to be a function of time. And once you have this differential equation, you solve this differential equation, okay, and while solving, after solving, you put the output voltage as equal to half of the supply voltage, and the time at which it happens is your propagation delay inside a IC. Okay. So, as already explained, this differential equation is going to be based on charging and discharging of the wire capacitor. This switching behavior, once it charges say from 0 to some final value and then it discharging from final to some initial value. This switching behavior takes time. Okay. So, the charge which the capacitance is holding, the wire capacitance is holding, can be written as Q equal to C V. This is already a very well known equation. So, charge is proportional to the amount of voltage which is present across the plates of a capacitor, and the proportionality constant is the capacitance. It basically measures how much charge the capacitor can hold. If you differentiate the equation on both sides to obtain current, so the current which flows through the or carried by the capacitor is C dV by dt. Okay. So, dV by dt is the rate of change of the voltage across the capacitor. Okay. I is your charging current, C is the capacitance. Okay. So, the solution of this differential equation is basically what is known as transient analysis or transient response, and this response provides us with a value of propagation delay. In an integrated circuit, capacitance can be obtained from different sources. It may be present because of different things, the way the IC is fabricated, the layers it has or the material it uses, okay, or the way the interconnects are connected. Largely you have the gate capacitance of the load transistor, the MOSFET which is being driven, okay, the diffusion capacitance of the transistor which is driving the load, and the wire capacitance which is connecting the two transistors. Okay. And the drain to source current depends upon this input as well as output voltage. The voltage you apply on the gate, okay, and the voltage you apply on the drain terminal, these two voltages basically decide how much drain to source current flows. Okay. So, to understand this entire transient response or transient analysis, we take one very common example of that of an inverter. Okay. So, the circuit which is shown on your screen has an inverter at end A, node A, which is driving another inverter, okay, via a wire at node B. So, you have one inverter x 1, another inverter x 2. So, x 1 can be considered as your driver inverter, x 2 can be considered as the load. Okay. So, you can see one PMOS connected in series with another NMOS. So, your PMOS is your pull up transistor, it pulls the output up to power supply, okay, or VDD. Then you have an NMOS transistor which is your pull down transistor which pulls the output towards ground potential. Okay. So, when your A node or point A at x 1 is at high voltage, your N 1 turns on and drives node B to ground potential. Similarly, when A is at ground potential or 0 logic, it is going to turn the PMOS transistor on and it is going to pull the node B or the output of x 1 to power supply. Okay. So, for us when you are doing this transient analysis, our objective is to compute how much time it takes, how much delay is introduced at node B here at node B when A is stepped up from 0 to VDD. VDD is generally plus 5 volt power supply. Okay. So, when initially when A is at 0 ground voltage, when it is pumped up to some positive voltage, after how much time the logic state of B changes state, that is a propagation delay. Okay. So, this figure is basically a capacitive version of your inverter. Okay. These are some of the symbols of capacitances which you can encounter in an IC. So, you have diffusion capacitance between source and body or substrate, diffusion capacitance between drain and substrate, some gate source capacitance at the load, okay, and wire capacitance which is connecting point A to point B, okay, which is also considered as part of the load. Now, since we are talking about charging and discharging of the capacitor, okay, only those capacitances which are either connected to node B or not connected to constant voltages are going to produce switching delays. For example, there is a capacitance between source and body for both PMOS of x 1 and NMOS of x 1. These are connected to constant voltages. Source to body capacitance of P 1 is connected to VDD. The source to body capacitance of N 1 is connected to ground. Now, these are constant voltages. So, there is not going to be any kind of a charging or discharging. So, there is no issue of delays here. Okay. The diffusion capacitances of the load they are not connected to point B. So, they do not contribute to any kind of a delay. Only the diffusion capacitance between source and body or between drain and body of the driver transistors, driver inverter, and the wire capacitance and the gate source capacitance at the load, okay, for P2 and for N2. Okay. These are the ones which are going to contribute to delays. So, only the drain to body capacitance of X1, wire capacitance and gate to source capacitance of X2 produce switching delays. Okay. These can be considered as to be connected to a certain point, node B, and the other terminal grounded for reference. Okay. So, this can be considered in an equivalent terms, it can be considered as a network of capacitors connected in parallel, right. And when capacitors are connected in parallel, the equivalent capacitance is an addition of all the individual capacitances. So, the net capacitance or output capacitance which is appearing at node B or the output of inverter X1 is an addition of all these drain to body capacitances at X1, the wire capacitance and the gate to source capacitance at the load. So, this is your net output capacitance. This net capacitance is what is the source of propagation delay. Okay. So, once you apply initially when A point, A node is at 0 volt, okay, at logic 0, N1 is off, P1 is on, PMOS turns on at low voltages, NMOS turns on at high voltages. So, initially N1 is off, P1 is on. So, your node B is pulled up to power supply. Now, this is inverting action, we are talking about inverters here. Okay. So, when 0 is at the input, 1 should appear at the output. When A is ramped up to logic 1 to some positive value, now NMOS turns on in X1 and PMOS turns off. So, B drops to 0. The time it takes, the rate at which your output voltage is changing is given by this equation here which is C out, output capacitance, we have already calculated the expression for it. Rate of change of output voltage at node B is equal to minus of the drain to source current flowing at N1. Okay. So, you have initially you have voltage 0, okay, 0 logic at node A of X1, right, and then you ramp up that value to logic 1, and then it takes some amount of propagation delay for node B to change its state. And this equation which you are seeing on your screen basically tells you how much is the role of the output capacitance in the total rate of change of output voltage. Okay. Now, the gate is at VDD, the source becomes at equal to 0, the drain is at V out, we are talking about the transistors connected to node B. Okay. So, VGS is equal to VDD, okay, and VDS is equal to V out. Initially, your drain to source voltage when node A is at 0 volt. Okay. So, VDS is equal to VDD, which is much higher than something which is known as gate overdrive. So, VGS minus VT, where VT is the threshold voltage, the voltage above which your NMOS turns on or the voltage below which your PMOS is considered on. Okay. This gate overdrive. Okay. So, the voltage at the output is higher than the gate overdrive. So, N1 is in saturation. Okay. As V out falls below VDD minus VT, your N1 enters the linear regime. Okay. So, if you remember the working of a MOSFET, it is not a linear device, it starts in a linear region and then it moves on to saturation. Right. In saturation, the output current is not a function of the drain voltage, okay, but in linear region it is a function of the output current varies linearly with output voltage. That is also a reason your MOSFET is considered as a voltage controlled current source, because it provides constant current during saturation. So, the two equations which come to us or which become available to us depending upon the mode in which N1 is located, whether it is in saturation or whether it is in linear region. If it is in saturation, we are looking at the equation on top. This is when your N1 is in saturation, okay, and this when your N1 is in linear region. Okay. So, these are the two differential equations which are available to us. You solve them, you get the transient response, put V out equal to half of VDD, you get the propagation delay, right. Now, it's usually a difficult task to solve differential equations at times. If you look at the equation on the previous slide, right, you have a square term in one of the equation and then you have a long linear term in another equation. At times it becomes difficult to solve all the differential equation, you need something more simpler. This is where we use RC delay model. Okay. So, what do these RC delay model do? They take into account the non-linearity of a MOSFET, the IV, the CV characteristics, they are not linear, they are non-linear. So, it quantifies something called an average resistance and an average capacitance, and it uses that average values of resistance and capacitance to obtain the delay, right. And this is to provide more simplicity to calculation of propagation delays. The RC delay model, it treats a transistor which is nothing but a capacitor, it is charging and discharging that capacitor as a switch in series with a resistor. Okay. So, every circuit can be considered as a series RC circuit. It has a certain effective resistance, okay, ratio of drain source voltage to drain source current, right. And we define something which is known as a unit transistor. So, we define a unit NMOS transistor which has certain effective resistance R, and we define a unit PMOS transistor which has a certain resistance of 2 R. Okay. Why this factor of 2? The origin of this factor of 2 is because PMOS have majority holes. Conduction in a PMOS transistor is because of holes. Conduction in an NMOS transistor is because of electrons, and because of the energy band models, holes tend to have lower effective mass and hence higher effective mass and hence lower mobility. Okay. So, holes tend to be heavier as compared to electrons. This produces lower hole mobility as compared to electron mobility, right. And since in a CMOS circuit, a complementary MOS circuit, we want symmetry. Okay. We want the PMOS circuit to be analogous or complementary to an NMOS circuit, right. So, we deliberately have or model higher resistance for a PMOS circuit as compared with NMOS. So, that we have a symmetry when a signal is rising or it is falling, it should have equal timing. Okay. So, your unit NMOS and PMOS transistor, just like resistance, they also have an effective capacitance, right. And what is a unit NMOS and unit PMOS transistor is? It is a model of an NMOS transistor whose width is unity, a modeled PMOS transistor whose width is unity. And if you scale the width, either increase it or decrease it, the resistance becomes lower with increasing width and the capacitance becomes higher with increasing width. So, the figure shown on your slide is actually of a PMOS. First, this is an NMOS. So, you have a NMOS symbol and you have a PMOS symbol. Okay. So, you have a resistance here and divided by K, because your resistance is rho L by thickness times width. So, we are talking about this width here. When width increases, your resistance reduces. Okay. Capacitance is directly related to width, right. So, if you multiply the width by a certain factor K, where K is higher than 1, resistance reduces and capacitance increases. Okay. So, everything is defined in terms of unit MOSFETs, unit PMOS, unit NMOS. A unit NMOS transistor or a PMOS transistor has resistance R, okay, and a unit capacitance C. The only difference being that a PMOS transistor is going to have a higher resistance due to lower hole mobility. So, as an example, we take an example of a unit inverter. Okay. When I say unit inverter, it means the PMOS transistor is going to be a unit transistor, okay, and an NMOS transistor is also going to be a unit transistor of width unity. Okay. So, the first thing, we write a number 2 in front of PMOS, which basically says that the capacitance is twice of that of a unit transistor and the resistance is same as that of a unit NMOS transistor. Okay. So, if you are going to increase the width of a PMOS transistor, the resistance is going to be reduced by half. Okay. So, in this unit inverter, the pull up network, the PMOS transistor is going to have twice the width, which means half the resistance, okay, of a NMOS transistor. And because of lower hole mobility, we are deliberately increasing the resistance of a PMOS transistor, okay, to account for these dissimilarities in the mobility, and this provides us with a complementary circuit. Okay. So, only the capacitances connected to the output node, they contribute to delays. Those capacitances which are connected to constant voltages, these are called non switching capacitances, they are not relevant for us. So, in output at a time only one resistor is active. So, you see resistance here, okay, and 6 times C, this 6 times C comes from twice the capacitance here, twice here, C here and C here. Okay. So, 2 C from the 2 PMOS transistors, okay, and 1 capacitance from the NMOS transistor. Okay. Similar thing can be applied to an RC model of a 3 input NAND gate. Here, because at a particular time only one PMOS transistor can be turned on for logic 1. So, you just use a unit PMOS transistor of twice the width of a unit NMOS transistor. But for logic 0 at the output, you need 3 transistors to be on in series. So, you design the transistor such that it has the width 3 times of that of a unit N MOSFET. Okay. So, that each MOSFET is going to contribute 1/3 of the resistance. Okay. Right. Finally, let us take up one example of how to, now we have seen how to get the resistance and capacitance for any circuit, how we use it, okay, how we actually calculate the propagation delay. Right. So, this is an example given to you. A particular interconnect or a wire has been modeled as an RC circuit. A step input is applied at the input called V in and output is measured across the capacitor. If I apply Kirchhoff's voltage law to this circuit, my input voltage is nothing but an addition of voltage across resistor and voltage across the capacitor. Now, voltage across resistor simply according to Ohm's law is I times R. So, I write R, and since R and C are connected in series, I just take the current across through the capacitor, okay, and that is given by C into d V out by dt, and the voltage across capacitor is nothing but my output voltage. This is the differential equation of an RC model. Now, I need the transient analysis. Okay. For transient analysis, I need to do a bit more extra analysis. So, when I have this equation, if I take the Laplace transform of this equation here, if I apply Laplace transformation, okay, and use the derivative identity, I can get the transfer function of this circuit. Okay. This is the transfer function of this circuit. The transient response in principle is nothing but output voltage in the time domain. So, now I apply the inverse Laplace transform, right, to obtain the transient response. So, if I have this transfer function, I apply inverse Laplace transformation, I am going to get some kind of equation like this, which basically tells me that my output voltage is exponentially decaying, right, and that decay can be controlled either by RC or V in. Propagation delay by definition is when my output voltage is half of my input voltage. So, I change the voltage at my input, I observe when 50% of that appears at the output. The time it takes for that to happen is the propagation delay from the input to the output. Okay. So, in this equation, if I substitute V out as equal to V in by 2, Now, my time becomes equal to the propagation delay. Okay. Small mathematical analysis is going to tell me that the time it takes for 50% of my input change to appear at the output is going to be R c times natural log of 2. Okay. So, almost 0.7 times or 70% of the R c time constant. So, okay. So, this is where R c delay model increases the simplicity of calculating the propagation delay across an interconnect. Okay. This is a much more simpler approach as starting with a differential equation and then solving that differential equation and then putting the value of half of the input voltage for output. Okay. So, instead of doing that, we model the circuit as a series combination of a resistance and a capacitance, do some small circuit analysis which is much more simpler than solving a differential equation. Okay. And then when you substitute your output voltage as half of your input voltage, you get what is known as the propagation delay. Okay. So, that is the end of this lecture. Right. Thank you.